Thank you for being here today. Today I'll be talking about LWeb, which is a secure information flow control system for SQL-backed web applications. This is joint work with Nikki Vizou and Michael Hicks. So why do we care about information flow control and LWeb? Well, many modern web applications need to protect confidential, sensitive information such as health and financial records. It's important that these applications protect the integrity and confidentiality of this data. Traditional mechanisms like manual access control can leak or corrupt information through implementation mistakes. So information flow control is one solution to this problem. It's a systematic approach that restricts how information flows through a program. So in this work, we focus on protecting flows between SQL databases, servers, and clients. So here's an example of information flow through a database. So if a secret is true, we decide to insert a row into the database. Otherwise, we don't do anything. And this is an observable difference based off of secret information. So in LWeb, we want to prevent these types of flows. So there are many different approaches to information flow control. Some techniques statically enforce this property, and others add dynamic runtime checks. And there are various trade-offs to these approaches that include expressibility, performance, and correctness. LWeb does well in these areas by offering expressive policies, efficient queries, and a mechanized formalism. And this formalism was actually useful in that it revealed 2 bugs in our original rules before we had the formalism. So these are our contributions. LWeb has an implementation that integrates with Yesod, which is a popular Haskell web framework. We have a case study where we used LWeb to with a build a break it fix it website. We have a formal model that adds support for SQL database queries. And we have a mechanized proof of noninterference, and we did this using Liquid Haskell. So I'll start with giving some background on LIO and Yesod. So LWeb builds on top of LIO. So this is an existing information flow control system. And in LIO, data is annotated by some security labels. So an example of a security label might be public or secret. So labels don't only have to be public or secret. They can be generalized to any security lattice. And the security lattice needs to implement a partial ordering or a can-flow-to relationship and meet and join operations. On the right, you can see how this lattice is implemented as a Haskell type class. So LIO enforces noninterference. So this is a property that states that an adversary at a label L1 can learn nothing about data labeled with L2 when L2 does not flow into L1. So as an example, a public user cannot learn secret information since secret does not flow into public. So LIO enforces security using the LIO-monad. This is a drop-in replacement for Haskell's IO-monad. And it performs information flow control checks at every single effectful operation. So for example, every time you enter the network, read from the file system, et cetera, it'll do a check. LIO dynamically tracks security using a notion of a current label. So this current label is the join of all labels of all values read in the current scope or in the current computation. So here's an example illustrating the current label. So initially the current label is public. We read from a public channel, and the current label stays public because public join public is public. So now we're going to read some secret information. So now the current label increases to secret because secret join public is secret. Now if you try to write to a public channel, well, this isn't allowed, right? Because we've read secret information and we're trying to write it to a public channel. This throws an exception because secret does not flow into public. So in LIO, data can be stored inside of these labeled boxes. values inside labels boxes cannot be read directly. So you have to explicitly open them, which will raise your current label. And at the top, you can see two functions that will box and unbox labeled values. And here's another example. Basically, anytime you label a value, it's like writing to that channel. And when you unlabel, it's like reading from that channel. So this is similar to the previous example. So Yesod is a web application framework for developing type-safe web applications. So it provides a DSL to define database table definitions. So at the top, you can see the definition of the friends table. The friends table has 3 fields, user1, user2, and date, and they all have type text. Yesod will, using template Haskell, will generate Haskell data types so that the programmer can use them in their application. And you can see an example of what this might look like on the right. And it will also automatically generate a type for the primary key of that table. So you can run queries using Yesod. Here's a basic example where we use the get function to look up, given a friend ID, which is the primary key for the friends table. And using the friends date function, we extract when that friendship began. SQL also supports more expressive SQL queries with this library called SQLetto. So for example, you could do inner joins, outer joins, conditionals, etc. And at the top, here's an example of doing an inner join between the friends table and the user table. So I'll start talking about LWeb. In LWeb, we allowed the user to write database policies by writing label annotations. So this is an extension of the DSL that Yesod provides. And you can see these label annotations in blue on the top right. I'll explain these more in detail, but in the left-hand side of the label annotation protects the confidentiality of the data, while the right-hand side protects the integrity of the data, or the ability to write to that data. So here, label annotations, they can depend on either constant labels, the value of another field in the same row, or the row's primary key. You can also have the join and meet of all these different labels, and these labels are lattice ordered, and the programmer is responsible for implementing them according to the type class that I showed previously. And the implementation must also satisfy various laws that I will describe later. In the label annotations, you can define a table labels. So this protects the length of the table. So for example, for our friends table, the label annotation is bottom admin. So anyone can learn the length of the table. So anyone can do queries on this table. But only administrators are allowed to insert or delete rows from this table. We also have field labels. This protects the data in an individual field. So for example, the label for the date field is Alice meet Bob. So only Alice or Bob is allowed to read this date field. And the integrity part is admin, so only admins are allowed to write to this field. And on the right, you can see like an example of what this lattice might look like for Alice and Bob. So we define a dependency field as a field that is referenced by another field's label annotation. So for example, in the date label annotation, you see user1 and user2. So this means that user1 and user2 are dependency fields. And to ensure noninterference, we require these database invariants. The first is that the table label must be constant. The second is that dependency labels must be constant and flow into the table label. And third, labeled or box values cannot be directly stored in the database. And we enforce these invariants statically at compile time using template Haskell. So we have a formalism in Haskell. And this formalism uses Liquid Haskell. So Liquid Haskell is an extension of Haskell types with refinement types. So you can see an example of division, and we extend the type for the denominator to be not equal to 0. And type checking is automated by an SMT behind the scenes. So from work last year, this added a refinement reflection to Liquid Haskell. So this allows refinement types to express arbitrary theorems. So for example, we have an idempotence theorem on the erasure function. So erasure function is just a regular Haskell function. And we have a theorem that the erasure of the erasure equals just the erasure. And proofs in Liquid Haskell are explicitly provided as Haskell functions. So these are the label laws I alluded to earlier. We defined them using refinement types in Liquid Haskell, and we've extended this type class that I showed earlier. So for example, we know that can-flow2 must be reflexive and transitive. So we've defined that in our refinements, and we also define join in our refinements. So we use these label laws throughout our proof. Here's an example of proving a basic lemma, and we use them by just calling them in the Haskell body. And then we have this question mark proof combinator to combine both proofs together to create a bigger one. So we define the semantics of LWeb using an interpreter. This is just a Haskell function. So here we define the label function and the unlabeled function. And you can label a value as long as the current label flows into the box label. Otherwise, an exception is thrown. And you can unlabel something as long as you join the current label by the box label. So in our formalism, we define semantics for database operations of insertion, selection, deleting, and updating. But today, I'm just going to go through insertion and justify the rules and why we have them. So here, this is a naive implementation. We take two labeled values, and we create a row out of them, and we insert them into the database. So let's look at an example of why this is a bad idea. Let's assume that the table label is public. So this is the same example we saw earlier. If we have some secret data, we're going to insert this row into the database. Otherwise, we're not going to do anything. So again, we have an observable difference in the public table length. Based on if the secret is true, then we insert the table length is 1. Otherwise, the table length is 0. So we want to prevent these implicit flows into the table. And we do this by inserting this additional check that the current label must flow into the table label. So here's another example. In this case, let's assume that the field label for the label for field 1 is public. And we have some secret valuable val1. So we're inserting secret value val1 into the public field field 1. Again, this creates a leak of information from a secret level to a public level because the field is public and anyone at public level can read this. So we want to prevent this kind of information flow again. So we insert an additional check that the box label must flow into the fields label. So one more example. Let's assume that the field label is secret, and the label of field 2 is actually field 1's value, right? So now we have a dependency between the labels and in the current row. So let's have a value val1. This is a labeled secret, and let's assume its value is label1, some variable. So let's assume label1 is public. So now we're trying to insert secret data into a public channel. So from our rules earlier, we know this is unsafe. So an exception is going to be thrown, and execution will stop. And we will never do this bottom right to the public channel. Now let's assume the other case where the label is secret. In this case, we're writing secret data to a secret field. And this is allowed. But this time, execution will continue, and we will actually do this right to the public channel. So this creates an observable difference to a public channel, again, based off secret data. So to prevent this, we're going to join the current label with the label of box 1. So I'll give a brief overview of our proof in Liquid Haskell. So in our proof, we use erasure, which erases sensitive data above a given label and replaces it with a hole. So this helps us determine low equivalence, which basically states that programs are indistinguishable except for their secret data. And here we see an example of two terms that are equivalent except for their secret value, but we know that they're low equivalent since their erasures are equivalent. Here's our statement of noninterference in Liquid Haskell. So we have two programs, P1 and P2. We have a precondition that the erasure of P1 equals the erasure of P2. And this returns a proof that the evaluation of P1 is low equivalent to the evaluation of P2. So here's our proof body. It's pretty simple. It relies on a simulation theorem. But we know that the first line equals to the second line due to the simulation theorem. We know that the second line equals the third due to the low equivalent precondition. And the third and fourth are equal, again, due to simulation on P2. So we have a case study where we integrated LWeb into a website called Build It, Break It, Fix It. This is a contest website where participants are able to submit code and basically attack each other's submission. So this website is over 11,000 lines of Haskell code. It's made up of 48 database tables. It has various roles such as participants, teams, judges, etc. So we measured the overhead between a version of this website with LWeb and a version without LWeb, and we measured overhead between 2% and 21%. So here's a graph of the throughput of both versions of the website. The version in red is the LWeb version. Y-axis is throughput. And the x-axis is different pages on the website. So you can see that the throughput is slightly lower for the LWeb version, but it's not that much slower. So in summary, these are the advantages of LWeb. It's expressive. It allows the user to define database policies using label annotations. The user can write expressive SQL queries that supports a large subset of SQL. It's performant. It only has a 2 to 21% overhead. And we offer guarantees of correctness with our mechanized formalism. And again, this was actually useful in that it revealed 2 real bugs in our original rules. So this is our future work. We'd like to expand our formalization of our database query language. We would like to mechanize the shell embedding, so the actual implementation of LWeb. We would like to add more support for more precise declassification techniques. And we'd like to improve the usability of Liquid Haskell for metatheoretical proofs. So if you're interested in working on this, come talk to me or Nikki. So in conclusion, I've given you a background of LIO and Yesod. I've talked about LWeb and its abilities to define policies using label annotations. I've gone over our formalism and discussed the semantics for insertion. And I've given an overview of our proof. And this is the first metatheoretical proof in Liquid Haskell. And we went over the Bibify case study. Thanks.
Okay, so we have microphones for people who'd like to ask questions from the audience, but we also have Slido where you can ask anonymous questions if you'd like. So let's start with a Slido question. And one of the questions here asks, do you know what the limitations of your database labeling policies are? So what kinds of policies might one like to express that you can't express?
So I guess probably the biggest limitation is that you can't have labels that depend on values inside other tables. But I think in practice you actually want this because this would be bad for performance because you'd have to do a query on another table every single time you want to look up that table. And I don't think you could easily enforce noninterference doing that. So.
This is very cool because it begins to draw a link between all the work we've done on proving things in stuff like Agda and Calc and being actually able to do proofs for working Haskell software.
Right.
So that's very exciting. You said you did a proof in Liquid Haskell.
Mm-hmm.
You didn't say much about it, and you did hint that you'd want things to be better. So how hard was it to do this proof compared to using something like Agda, and what other steps you want to take to make this easier?
Mm-hmm. So I'll say that this is the first metatheoretical proof in Liquid Haskell. So we hit some, I guess, snags along the way. There was one performance issue we ran into. And we, patched Liquid along the way to help support this. And I've done a little bit of proving in Calc, but most of my experience is writing Haskell, so it was actually good for me as mainly a Haskell programmer to do this proof. So I'm hopeful the general Haskell community will be able to use this and integrate this with their systems.
Okay, I think we have time for one more quick question.
I was actually a little confused by that question from Phil. So my understanding of the work is that you built a formal model of LWeb and proved non-interference about it,
right.
rather than using Liquid Haskell to prove the security of the software you implemented.
Right. So
right?
this is a future work, next up, that we'd like to do.
All right, well, thank you very much.